Good evening, students. Welcome to 11th Standard Chemistry video class. We are discussing Lesson 7 Thermodynamics. In this video, we are to discuss the next topic, internal energy. Here, we have to discuss definition for internal energy, importance of internal energy, and characteristics of internal energy. First, let me discuss the definition for internal energy. Internal energy. The internal energy is a characteristic property of a system which is denoted by the symbol U. Again I repeat, the internal energy is a characteristic property of a system. The internal energy is denoted by the symbol U. The internal energy of a system is equal to the energy possessed by all its constituents, namely atoms, ions and molecules, which means the internal energy of a system is equal to the energy possessed by the system which contains atoms, ions and molecules. The total energy of all molecules in a system is equal to the sum of their translational energy UT, vibrational energy UV, rotational energy UR, bond energy UB, electronic energy UE and energy due to molecular interaction UI. Again I repeat, the total energy of all molecules in a system is equal to the sum of their translational energy, vibrational energy, rotational energy, bond energy, electronic energy and energy due to molecular interaction. Thus, U equal to UT plus UV plus UR plus UB plus UE plus UI. Again I repeat, the internal energy U is equal to UT plus UV plus UR plus UB plus UE plus UI. The total energy of all the molecules of the system is called internal energy. The total energy of all the molecules of the system is called internal energy. In thermodynamics, one is concerned only with the change in internal energy rather than the absolute value of energy. In thermodynamics, the change in internal energy delta U is considered rather than the absolute value of energy. Next, let me discuss the importance of internal energy. Importance of internal energy. The internal energy possessed by a substance differentiates its physical structure. The physical structure of a substance is differentiated by the internal energy possessed by a substance. For example, the allotropes of carbon, namely graphite and diamond, differ from each other because they possess different internal energies and have different structure. Here, graphite and diamond are allotropes of carbon. They differ from each other because graphite and diamond possesses different internal energies and they have different structure. It is to be given for importance of internal energy. Next, let me discuss the characteristics of internal energy. Characteristics of internal energy. The following points are the characteristics of internal energy. Let me discuss one by one. First point, the internal energy of a system is an extensive property. It depends on the amount of the substance present in the system. If the amount is doubled, the internal energy is also doubled. Here, the internal energy of a system is an extensive property. Already, we studied about the extensive property. The property that depends on the mass or size of the system is called an extensive property. Hence, internal energy depends on the amount of substance present in the system. If the amount is doubled, the internal energy is also doubled. Second point, the internal energy of a system is a state function. It depends only upon the state variables T, P, V and N of the system. The change in internal energy does not depend on the path by which the final state is reached. Here, the internal energy of a system is a state function. It depends only upon the state variables, namely temperature T, pressure P, volume V, and the number of moles N of the system. Change in the internal energy, that is delta U, does not depend on the path by which the final state is reached. Third point, the change in internal energy of a system is expressed as delta U is equal to UF minus UI. The change in internal energy of a system is given by delta U is equal to UF minus UI. Here, delta U is change in internal energy, UF is internal energy for final state, UI is the internal energy for initial state. Fourth point, in a cyclic process, there is no internal energy change. Delta U for a cyclic process is equal to 0. For a cyclic process, there is no change in internal energy, that is delta U for a cyclic process is 0. Fifth point, if the internal energy of the system in the final state UF is less than the internal energy of the system in its initial state UI, then delta U would be negative. Delta U is equal to UF minus UI, which is equal to negative, in which UF is less than UI. Here, the change in internal energy is calculated from the formula delta U is equal to UF minus UI. If UF is less than UI, then the change in internal energy delta U becomes negative. Sixth point, if the internal energy of the system in the final state UF is greater than the internal energy of the system in its initial state UI, then delta U would be positive. Delta U is equal to UF minus UI, which is equal to positive if UF is greater than UI. Here, the change in internal energy is calculated from the formula delta U is equal to UF minus UI. When UF is greater than UI, then change in internal energy delta U becomes positive. Hence, we completed the characteristics of internal energy. Next, let me discuss heat and work. First, let me discuss heat. In this topic, heat, we have to discuss the definition for heat, units for heat, and sign convention of heat. First, let me discuss the definition for heat. Heat is denoted by the symbol Q. The heat is regarded as an energy in transit across the boundary separating a system and surrounding. Heat changes lead to temperature differences between system and surrounding. Heat is a path function. Here, heat is a form of energy which is transmitted through boundary which separates system and surrounding. The temperature differences between system and the surrounding is given by heat changes, where heat is a path function. Next topic, units of heat. The SI unit of heat is joule. Again I repeat, the SI unit of heat is joule. The heat quantities are generally measured in calories. Here we are having the definition for calorie. A calorie is defined as the quantity of heat required to raise the temperature of 1 gram of water by 1 degree Celsius in the vicinity of 15 degree Celsius. Again I repeat, a calorie is defined as the quantity of heat required to raise the temperature of 1 gram of water by 1 degree Celsius in the vicinity of 15 degree Celsius. It is to be given for units of heat. Next topic, sign convention of heat. The symbol of heat is Q. If heat flows into the system from the surrounding, the energy of a system increases. Hence, it is taken to be positive, that is plus Q. Here, if the heat flows from surrounding to system, the energy of the system increases. Hence, the heat Q is taken as plus Q. Next one, if heat flows out of the system into the surrounding, the energy of the system decreases. Hence, it is taken to be negative, that is minus Q. Here, if the heat flows from system to surrounding, the energy of the system decreases. Hence, the heat Q is taken as minus Q. Hence, we completed the definition for heat, units for heat, and sign convention of heat. Next, let me discuss work. In this topic, work, we have to discuss the definition for work, the characteristics of work, the unit of work, and the sign convention of work. First, let me discuss the definition for work. Work is denoted by the symbol W. Work is defined as the force F multiplied by the displacement X. Again I repeat, work is defined as the force multiplied by the displacement. Equation 7.1 gives the mathematical expression for work. Minus W is equal to F into X. Again I repeat, minus W is equal to F into X. The negative sign is introduced to indicate that the work has been done by the system by spending a part of its internal energy. Next, let me discuss some characteristics of work. First point, work is a path function. Already we discussed that work is a path function. Second point, work appears only at the boundary of the system. That is, work to be done only at the boundary of the system. Third point, work appears during the change in the state of the system. That is, if there is change in the state of the system, the work will appear. Fourth point, in thermodynamics, surroundings is so large that macroscopic changes to surroundings do not happen. Hence, we completed the characteristics of work. Next, let me discuss the units of work. Units of work. The SI unit of work is joule. Again I repeat, the SI unit of work is joule. Here we are having the definition for joule. Joule is defined as the work done by a force of 1 Newton through a displacement of 1 meter. Again I repeat, joule is defined as the work done by a force of 1 Newton through a displacement of 1 meter. That is, joule equal to Newton meter. We often use kilojoule for large quantities of work. That is, 1 kilojoule is equal to 1000 joule. Next, let us discuss the sign convention of work. Sign convention of work. The symbol of work is W. If work is done by the system, the energy of the system decreases. Hence, by convention, work is taken to be negative, that is minus W. Here, if work is done by the system, the energy of the system decreases. Here, it is given by minus W. Next one, if work is done on the system, the energy of the system increases. Hence, by convention, the work is taken to be positive, that is plus W. Here, if work is done on the system, the energy of the system increases. Here, it is given by minus W. Hence, we completed the definition for work, characteristics of work, units of work, and sign convention of work. Let me stop up to this topic. The remaining topics that we will discuss in our next video class. Thank you.